So yesterday we covered experimental probability and how experimental probability is different than theoretical. If we go back to it, theoretical probability is what should happen. So for instance, if you're tossing a coin, which has two sides, the probability of landing on heads is 50-50 or 1/2 or 50%, whichever way you want to think about it. Versus the experimental probability is what actually happens. So let's say a coin was tossed 100 times and heads appeared 60 times. Therefore, the probability of landing on heads according to this experiment is that the next toss is 60 out of 100, which simplifies to 6/10, which simplifies to 2/5. So you have a 2/5 chance of getting a heads, versus the theoretical, which is 50-50. So not always going to be exact, but pretty close. If you think about 60 times out of 100, that's really close to 50. So if we look at an experiment, which we'll do a mini version in class, but I just did it just before the video started. I flipped a coin 20 times and I tallied how many times I got heads and how many times I got tails, and I got heads 11 times versus tails 9 times. And when I tell you that it was neck and neck throughout the whole experiment, it is really close to being 50-50, which is what should happen. But in my experiment, I got 11 out of 20 versus 9 out of 20 for my tails. So what's the comparable difference? Is that it's really close. Theoretical and experimental are really close and should go hand in hand, but not always. Why would they be different? Is because, you flip a coin, the odds are not necessarily in your favor. So it's just random. But what we're talking about today is somebody had already done the experiment for us. We just have to read those results. So if I look at number 7, a letter in the word XXL is chosen 50 times at random. What is the theoretical probability of choosing C? Well, the theoretical is what should happen. So this is where I count how many C's are in the word out of how many letters total, which is 5. So I have a 2/5 chance of getting a C when I draw for it, versus somebody who had done that and picked a letter at random 50 times. Here are the results. Frequency just means how many times. So they chose A 14 times, C 5, C 7, which means a total of that, which we'll talk about, E 15 times, and L 9 times. So what is the experimental probability of choosing a C? Well, according to their experiment, they had 2 C's, which means 5 plus 7, which is 12, out of the total, which was 50. And then I simplify this. 2 goes into 12 6 times, 2 goes into 50 25 times, and that's as far as I can simplify it. Now, at first glance, it doesn't look like it's much comparison, right? But if I try to make them the common denominator, 5 goes into 25 5 times, so 2 times 5 is 10. So now I can actually compare them. And it's really close to what theoretical probability would be according to the word Excel. If we look at another example, somebody spun this spinner on the left 80 times, and here are the results. But theoretically, what's the probability of not landing on polka dots? So if I look at my spinner here, I have 1, 2, 3, 4, 5, 6, 7, 8 sides, and 2 of them are polka dots, but we want the probability of not polka dots, so that means everything else. 1, 2, 3, 4, 5, 6. And if I simplify that, I would get 3 and 4, so 3/4 chance of not landing on polka dots. Versus if we look at not landing on polka dots according to this frequency table, it's 27 stripes, 18 polka dots, and 35 solid. I want not polka dots, so I want these 2, which when I add them up, is 62 times out of the 80 times. And when I simplify this, 2 goes into 62 31 times, and 2 goes into 80 40 times. And I can't simplify that any further. But if I really want to compare it, and I want them to have a common denominator, 4 goes into 40 10 times, so 3 times 10 is 30. So if you look at the comparison, they are actually really close in comparison. The number of times you would not get polka dots. 30 out of 40 here, but 31 out of 40 here. So really, really close.